All right, so we'll take a look now at one very important characteristic of organic compounds. That is, you really can't talk about organic chemistry and organic compounds without discussing this feature, this phenomenon, which is a phenomenon known as isomerism. And specifically here, what we're gonna, there are many different types of isomerism. We're gonna just focus on one basic type called structural isomerism. And as an analogy here, you can think of, if you remember, if you can Google this, the Transformers, registered trademark, a movie or the whatever, cartoons or whatever. So if you think about, that analogy, so if you can imagine, what everybody's favorite Transformer, like Bumblebee, for instance. Okay, it starts off as a whatever, a car. Okay, and then it undergoes some sort of a transformation. It becomes a robot. Okay, when it undergoes that transformation, what happens to it? Well, the components are the same when it goes from the car to the robot, but how they are attached, how the components are attached, becomes different. And as a result, okay, the robot here has a different structure compared to the car, but it has the same components. Okay, the same building blocks. And that's the exact thing that's going to happen when we talk about structural isomers in chemistry. That happens just like the transformer does, but on a much, much, much smaller scale. So for example, if we look at something like pentane. So pentane has 5 carbons in it, and there are 12 H's. Okay, this is the molecular formula. This is the types of formulas we've been using all along to represent compounds. So if we were to draw the structure for pentane, well, I have 5 carbons, so 1, 2, 3, 4, 5. And it's an ane, it's an alkane, meaning that the carbon to carbon bonds are all single bonds. I can fill those in. And then the remaining bonds are just the H's, right? So I'm just going to give as many lines to each of these carbons as I need to make sure that the carbon has 4 bonds, and I'm going to fill those into H's. Okay, so this, what I've just drawn here, is the structure for this regular old pentane. It's got 5 carbons and 12 H's. Well, especially as the size of the organic compound gets larger, this phenomenon of isomerism becomes more and more possible. So what we can do here is we can take these components and arrange them in a different way. So if instead of having 5 carbons in a row like this, what if I had 4 in a row? So 1, 2, 3, 4. And then I put a carbon coming off of the second one, like that. And then I fill in the remaining bonds to each of these C's to H's, right? And this one at the top here will need 3 more. So what do we end up with? Well, all I did was take 1 carbon out from one end and stick it on that second one. But if I look at the formula for this thing here, how many carbons do I have? Well, I have 1, 2, 3, 4, 5. So I have 5 carbons. How many H's do I have? Well, let's count them. So let's do a different color. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I still have my 12 H's, right? So the formula is the same molecular formula, but this structure here is different because now instead of having 5 in a row, I have 4 in a row. And then this one is poking out like a branch. So they're not the same. Even though they have the same chemical formula, they're different structures. These are structural isomers. Okay, so what structural isomers are are structure or things that have the same molecular formula, the same components, but different structures. Okay, and that is very common in organic chemistry. And a lot of times these isomers have different characteristics than the original one. You can probably imagine there's another one we can maybe draw. Okay, so instead of having four in a row, maybe if I had just three in a row, like this, and then I put a branch coming off of the middle one, and maybe another branch coming off of that same middle one. And then I fill in my bonds to H's, like so. So I give each of the carbons enough lines to give it four bonds, and I put my H's in for my structural formula. And what we will see here is if I were to count again, my carbons, I have one, two, three, four, five. Okay, so I have five carbons. How many H's do I have? I have one, two, three, four, five, six, seven, eight, nine, 10, 11, 12. So I still have my 12 H's. This is also a structural isomer of all the other two, right? They have the same formula. We've drawn all the atoms, all the bonds. They have the same components, just different structures. What if I had a structure like this one? Let's say I had one, two, three, four, and then maybe a C coming off of that one. Okay, then I fill in my H's. Okay, so each carbon needs four lines, four bonds to it. And I put my H's in like so. And then what we'll see again is I have now the same number of carbons. So let's see. So one, two, three, four, five C's. How many H's do I have? So one, two, three, four, five, six, seven, eight, nine, 10, 11, 12. So I still have my 12 H's. So now, obviously, this has the same formula as all the others, but is this different than any of the other three structures? Is it an isomer of those? Well, you may think it looks different, but it's actually identical to this one here. So this first one had five in a row. This one here also has five in a row. One, two, three, four, five. It's just that that fifth one is coming off at the top rather than to the left. So these are actually the same. These are identical. They're not isomers of each other. Okay, and this happens a lot with when you have carbon to carbon single bonds, right? This bond here, when you have a single bond, that's free to rotate around. So if I rotate this around, I end up with its other way here at the bottom, right? So carbon to carbon single bonds can rotate. And they can rotate freely. Okay, so this structure is the same as that. All right, they are identical structures because you have five in a row, cross five in a row, meaning five unbroken, one after another. In the other ones, we didn't have five in a row. All right, so we had was it four in a row here? And then the fifth one wasn't connected to the end. It was off of one of an interior carbon. And here we have three in a row, and then the fourth one is off the middle, and the fifth one is off that same middle one as well. Okay, so this phenomenon of isomerism, we just looked at one example, but as you can imagine, the bigger and the more carbons you have, the more isomers that are possible. And this gives rise to all these different possibilities of organic compounds that are on the planet, for example. And we are made of carbon compounds as well, right? There are all sorts of different types of isomers that we use. So, for example, some of the medications that you take for different conditions, your body is able to use one isomer of the drug and another isomer of that drug. The body doesn't even know what to do with it. It just gets excreted. So when medications are made in different chemistry labs, oftentimes these are really, really big molecules, and the active isomer of the drug needs to be isolated from all the other ones, and then that's the one that gets, administered. All the other ones don't do anything. Your body is that specific. It uses not just for like medications and stuff, but also foods and different types of things that you eat and drink. For fuel, your body's only able to recognize one type of isomer of these biological, biochemical compounds. So this phenomenon of isomerism is very, very common in organic chemistry. That's why we would kind of need to address it here. Okay. We'll take a look at this in a little bit more detail. I think we'll have a exercise on this in lab where you get to build some models and kind of explore this a little bit further as well.